I would like to introduce Hiruni Dassanayake, who will be talking to us about distal flows associated with the ejecta of Bamberg crater on Mars.
Distal flows associated with the ejecta of Bamberg crater on Mars. Can everybody hear me?
We can. You can go ahead and get started.
Okay. Yeah, thank you. So my name is Hiruni Dassanayake. I'm a science educator at the Overseas School of Colombo. Wait. Can you see the introduction page?
Yes.
Okay, thank you. So an extensive impact-related surface flow features were recently characterized around a small number of well-preserved impact craters on Mars, extending well beyond the continuous ejecta blanket. Distal flow deposits, or DFDs, have been described as outwards directed flows that responded to the topography of the target terrain. Initially, it was thought to be unique to a single large impact crater, Hale. Subsequent works have defined and characterized DFDs elsewhere on Mars. In order to better understand the prevalence and the emplacement mechanism of these novel deposits, Burley et al. Have carried out a global survey on Mars, shown in Figure 1, to identify the examples of DFDs and characterize the level of consistency between the impact sites. From Figure 1, you can see Burley et al. Have characterized 16 DFD-bearing craters as of 2024, and characterization of DFD-bearing craters have continued since. DFDs appear to occur quite ubiquitously across Mars, and DFD-bearing craters vary in sizes and levels of complexity. This study goes beyond the database of the DFD-bearing craters identified by Burley et al. In areas where a small number of DFD-bearing craters were identified in Arabia Terra. A late arriving ejecta emplacement was noted in the proximal region of Bamberg crater, located east of Acidilia planatia, extending towards the distal region. In this study, we look at Bamberg crater ejecta morphology and the consistency it has with other DFD-bearing craters on Mars. Based on the global database of the best preserved craters on Mars, Bamberg is a well-preserved crater that is slightly degraded, but is still readily recognized. The well-preserved crater studied by Burley et al. Bamberg crater could be an addition to the target properties, terrains listed in Figure 1 by Burley et al. Among the list of characterized sites with sufficient topographic variability. DFD-bearing craters have defined characteristics such as low slope angle, consistent with fluidized material, a preferential flow direction radiating away from the source crater, and DFD type 2 morphology that we later talk about in detail remain consistent across the dataset of identified DFD-bearing craters. These flows exist among the spectrum of DFD-bearing, well-preserved craters on Mars and are affected by topographic obstacles, but generally can be broken into two following morphologies. DFD flow type 1 on the left in Figure 3, impeded by crater-facing slopes, and DFD flow type 2, redirected into channelized topography. The individual flows are indicated with black arrows. The characterization of the distal flows features was done using CTX, HiRIX, and THEMIS data. THEMIS data and global CTX mosaic provide means to assess the crater flows and morphology of Bamberg. The target distal features were identified, which were followed with high-res images. This method is fairly consistent with the methods used in the previous studies conducted by Burley et al. Figure 4 shows a map of Bamberg with overlay of CTX and high-res images. The mapped facies units include continuous smooth Bamberg flow ejecta, distal flows, surface morphologies, and regions of exposed, relatively unmodified target terrain. The landscape modification associated with Bamberg ejecta emplacements in a morphological feature graben in Figure 8 was mapped using GMRs. In this study, the surface feature properties were mapped to understand the distribution, stratigraphic relationships, and morphology. This research focuses on flow types and deposits. Proximal continuous Bamberg smooth flow ejecta is shown in figure 5. Bamberg smooth deposits is shown in figure 6. And there's a high-rise stamp that's encircled in blue, which we will discuss later in detail. Bamberg distal flow deposit type 2 and Bamberg distal ejecta are drawn as two separate map units in figure 7. There's a key morphological feature. It is a Bamberg distal flow deposit type 2 overrides ejecta from the nearby unnamed crater in the preglacial surface morphological feature graben. The proximal continuous Bamberg smooth flow ejecta can be seen radial to the source crater, existing primarily outside of the said ejecta blanket in the muted terrain. Ejecta morphologically appear to be smooth in texture, as shown in figure 9. Figure 5 shows red arrows at the start of the proximal continuous Bamberg smooth flow ejecta. White line marks the boundary between the ejecta blanket and the continuous Bamberg smooth flow ejecta. Proximal continuous smooth Bamberg flow ejecta has over in its secondary craters, best observed north of Bamberg in a secondary crater chain. This is consistent with Hale HE2 ejecta as it provides strong evidence that these deposits were in place late in the crater formation process after the secondaries were already formed. Bamberg smooth deposits in figure 11 do not have a direct continuous Bamberg as it is placed on smooth Bamberg flow ejecta. This region of Bamberg figures. Bamberg smooth figure appear to be overlaid around
Apologies to interrupt. We're getting a breakup of your sound. Having trouble hearing you. You were a little bit better there, so maybe it's fixed.
Is it better now or?
Yes, that's much better.
Okay. So the Bamberg smooth deposits in figure 11 appear to be overlaying the ground-hugging proximal continuous smooth flow ejecta. It appears to be a discontinuous unit and could occur due to ballistic deposition related to the Bamberg impact process. More research needs to be done here. The deposits showed to be reacting to pre-existing positive topographic obstacles, shown in red arrows in figure 11. Bamberg smooth deposits could also be a source material that is channelized into the graben along with proximal continuous smooth flow ejecta that is radially expanding outwards from the Bamberg on the southwest region of Bamberg. This deposit could be traced back to the source crater. The channelized ejecta is an extended ejecta flow feeding the graben as CFT type 2, shown in red arrows. Figure 7 is right outside the distal region starting point, and it's consistent with DFD type 2, mentioned by Burley et al. In terms of their geographic constraint to the source crater, with the distal region modification generally extending from approximately 3 to 9 plus or minus 2 crater radii, regardless of the size of the crater. This is an example of flow materials that coalesce before channelizing into DFD type 2 in low slope surfaces above some morphologies as discussed by Burley et al. This is consistent with the work done by them where type 2 DFD characterizes flows that are generally observed where steep pre-existing slopes are associated with topography that create valleys. Additionally, because Bamberg DFD type 2 is in this morphological feature that is originating from Bamberg, smooth deposits and ground-hugging proximal continuous Bamberg smooth flow ejecta that is radially expanding outwards from Bamberg. The flow of the deposit could be traced back to its origin towards the source crater. Existing outside of the said ejecta blanket in a muted terrain and the continuous Bamberg smooth flow ejecta, Bamberg distal ejecta extend to more than 5 crater radii from the center of the crater. With the presence of subdued but readily identified distal ridges shown in figure 14, circled by light blue in the Bamberg distal ejecta can be seen in the southwest region of Bamberg and could exist radial to the source crater. A closer look at figure 14 shows a drop-off or cliff-like feature where the top black arrow is pointing. It could be expected DFD type 1 flows to be accumulated up against the ledge and smoothen the surface. However, there is a shadow near the drop-off and no fan-like accumulation of material, further supporting that it isn't a DFD Tab 1. Bamberg distal ejecta could be emanating from proximal continuous Bamberg smooth flow ejecta towards the distal region, drawn in light blue arrows in Figure 13, and is consistent with ballistic and aerial deposition. The Figure 15 shows the map of the morphological feature and the map key. The ejecta from the nearby unnamed well-preserved crater flows into the graben from the southwest region of Bamberg. Some of the unnamed crater ejecta is confined by the graben wall material. However, the unnamed crater ejecta flows beyond the unnamed crater ejecta blanket boundary and the graben wall boundary. Ejecta from the well-preserved unnamed crater appear to come before the Bamberg DFD Type 2 as it is overriding the unnamed crater ejecta. Bamberg DFD Type 2 flows right into the graben, overriding the unnamed crater ejecta, while the Bamberg distal ejecta does not flow into the graben. Existing towards the north and the northeast of the unnamed crater, Bamberg distal ejecta could have flowed over a part of the unnamed crater ejecta, graben wall boundary, and unnamed crater ejecta blanket boundary that appears to be at a relatively higher elevation than Bamberg distal ejecta. Bamberg distal ejecta is accumulated at the edges of its surrounding units, giving it a rougher surface texture than Bamberg DFD Type 2. However, Bamberg DFD Type 2 and distal ejecta appear to be smoother than the adjacent unnamed crater ejecta. Bamberg DFD Type 2 occurs right at the beginning of the distal region starting point and flows for approximately 42.5 kilometers inside the graben, up to 6.4 radii from the source crater. The elevation of the profile drawn on the unnamed crater ejecta in blue in Figure 16 reduces drastically when moving away from the unnamed crater ejecta boundary, where the lowest elevation recorded is minus 3,900 kilometers before eventually coming to a halt at minus 3,875 kilometers. The Bamberg DFD Type 2 elevation appears to remain constant at elevation approximately minus 3,870 kilometers from 17 kilometers to 19.75 kilometers in the elevation profile. This could indicate that Bamberg DFD Type 2 was a thin layer of distal ejecta that flowed and deposited over the unnamed crater ejecta. It remains low in elevation compared to the unnamed crater rampart and proximal ejecta. Initially, it was thought the Bamberg DFD Type 2 entered the graben and morphed into the DFD Type 1 as shown in Figure 18. Because visual characteristics of Type 1 DFDs have fan-like accumulation of material at the base of the topographic positive relief obstacles where there are outwardly mobilized material that accumulates at the bottom of the crater-facing slopes. However, a careful study and the mapping of the flow in the graben shows the interaction of two crater-related flows, one from Bamberg as Bamberg DFD Type 2 and another from a closer, small, unnamed well-preserved crater. This concludes that unnamed crater ejecta and Bamberg DFD Type 2 ejecta are distinctive crater-related flows independent of each other. The unnamed crater ejecta flow behavior strongly suggests it is in place through a ground flow mechanism and not aerial deposition. It appears to have deposited radially to the source crater. The surface roughness of the unnamed crater ejecta, drawn in green arrows, the direction of the flow in Figure 19 appears to be greater than the surface roughness of Bamberg DFD Type 2, drawn in brown arrows in the direction of the flow in the Figure 19. The brown arrows appear to flow over the green arrows from different arrow flow directions in the proximal region of the unnamed crater. There is discontinuation of Bamberg DFD Type 2 circled in red and thinning of Bamberg DFD Type 2 circled in purple in Figure 19. This could be due to erosion. This ties back to the preservation state of Bamberg, where Bamberg is a well-preserved crater that is slightly degraded, but is still readily recognized. Bamberg DFD Type 2 is originating from southwest direction of Bamberg, and unnamed crater ejecta is originating from the northwest of its source crater. The glacial deposits in Figure 21, showing the molar map, appear to flow downslope between boundary side walls and terminate in a distinctive tongue-like tongue as shown in Figure 23. It is located northeast of Bamberg and approximately 27 crater radii from the center of the Bamberg crater. The distinctive tongue may or may not feed into the higher-order ice-rich terrain type. Distal flows around Bamberg are not glacial deposits. However, certain characteristics of DFDs may appear similar to glacial deposit in a latitude similar to Bamberg location. Nevertheless, a closer look at these features shows there are distinctive morphological features that distal flows. This study is assessing. The deposit shown in the graben does not seem to be consistent with the glacial deposits due to morphological surface features and flow directions. Figure 24 lineation and linear textures in the direction of the glacial deposit flow that could indicate separate flow units. Figure 25 does not appear to have such lineations and textures. Hence, there could not be separate flow units in Bamberg DFD Type 2. Previous studies by Broly et al. Have shown there are no separate flow units noted in Type 2 DFDs. Variation in surface texture in the direction of the flow can be seen in glacial deposits, while variation in the direction of the flow cannot be seen in Bamberg DFD Type 2, and it's consistent in surface texture throughout the flow compared to Figure 24. The surface texture of the glacial deposits can vary significantly due to diverse nature of the deposited material. Some areas may have a smooth surface with fine-grained sediment, while small circles in red in Figure 25 could be boulders that were deposited during sediment transportation in glacial flow debris in the glacial deposit. The overall surface roughness in the glacial deposits is greater than the Bamberg DFD Type 2. This could be due to debris transfer during the deposition of the glacial deposits. The visual variations in surface roughness and surface irregularities in glacial deposits further distinguishes them from Bamberg DFD Type 2 that appear to be very smooth on the CTX and high-rise. In conclusion, the unnamed crater ejecta appear to enter the graben in filling in from the southeast direction. Careful mapping demarks the ejecta from Bamberg DFD Type 2 and unnamed crater ejecta to the southeast of the smaller graben. Bamberg DFD Type 2 is consistent flowing in a preferential flow direction, radiating away from the DFD-bearing source crater, and have defining characteristics such as low slope angle, consistent with the fluidized material that are similar to distal flow-bearing craters elsewhere on Mars. Bamberg DFD Type 2 in graben can be distinguished from preglacial flows found in graben all throughout this region by making a careful comparison of their surface morphologies and flow directions. The Bamberg falls into the range of crater diameter of the DFD-bearing craters studied by Burley et al. However, Bamberg is located more towards the northern hemisphere and beyond the previously studied regions. The location of Bamberg could add to the list of characterized sites with varying terrains by Burley et al. The observations of Bamberg DFD Type 2 morphology is remarkably similar to DFD Type 2 morphology, where it is consistent with the distal region modification, generally extending from approximately 3 to 11 crater radii, regardless of the size of the crater. This research shows an example of a DFD Type 2 with material accumulation. There has been some degradation, thinning of deposits, along with the lack of appropriate topography. This may explain why there weren't any DFD Type 1 that were identified. Bamberg crater is in an area where Burley et al. Had identified a very few DFD-bearing craters on Mars. Thus, based on the morphology and the terrain, it is very likely represents more degraded flow types and deposits than those previously studied. Hence, these deposits may be more ubiquitous than previously thought. Future works include better understanding the preservation states around Bamberg in relation to the location of the crater and identify more key morphological features that interact with late arriving distal flows and deposits. Thank you, and I'm open for questions now.
All right, if we would like to. We have lots of time for questions. So I am gonna look first for questions in the room for anybody, and then I know there's also a couple questions already online, so. Any questions in the room? All right, not seeing many.
No, I haven't.
Yep, go for it.
Yeah, so Veronica is asking me if I have performed any create accounts on separate DFD. Oh wait, I can't read this properly. But DFDs for Bambug. No, I haven't done create accounting for Bambug. So the flows are deposited are not. I haven't done create accounting for Bambug.
No worries. My question was mostly because a lot of your flows, you could tell that they were part of the distal ejector blanket, but then in figure 23, I couldn't quite work out where that was relative to the crater. It looked like an extremely far-flung flow. And so I guess the question is, how do you confidently link that back to Bamberg crater itself? Was it part of the ejector? We just couldn't see it in figure 23?
So let me see if I can find that slide. Wait. So how do I trying to okay. You said figure 23, is it?
Yes, that one.
Yeah. So
This
this
flow
is
is
not a distal flow. No. It's not a distal flow. It's a glacial deposit in the region.
okay. Good. Thank
Yeah.
you.
Any more questions?
I'm not seeing any here in the room. Double checking, making sure there's not any online. I think it was just Veronica's. All right, well, if we have no questions, let's thank Ernie again for excellent.
Thank you so much.
I think